Host disabled, participant screen sharing.
Oh, this is where I've got to make you the host again, by the look of it. So let me try that. I don't have any other options. I don't know how this happens on other. Okay, I'll change you to the host, so you should be able to do it now.
Right. Yeah.
There you go.
Okay. Let's go to the beginning. Can you see that okay? Robin?
Yes, it can be seen.
You can be seen, right. Okay. So this is a talk about viewing and imaging the planets. So I'll be talking about visual observing of the planets and a bit about imaging the planets and what you can see with visual observation versus what you can image. So when people start in planetary astronomy or starting in astronomy and view the planets for the first time, from having looked on the web and looked in various books, they might have an unrealistic expectation of what you might see. So here's various planets taken by the Hubble Space Telescope. You know, is that a reasonable expectation to see that level of detail from a telescope that you've bought and you're viewing from the back garden? Well, you really need to dampen your expectations. Your first glimpse of the planets are more likely to look something like this. So these are some shots that I took last week through my 18-inch telescope at the eyepiece with an iPhone to sort of mimic what you might see when you first put your eye to the eyepiece, and you've got Jupiter and Saturn there. Seeing and imaging fine details in the planets is difficult, but you can do that. Why is it so difficult? Why is it so tough to pick out the detail? And that's because the detail that you're seeing really is angularly very small indeed. So here's a high resolution, what you would regard as a high resolution image of the Orion Nebula there, showing a wealth of detail there, dark globules, you know, lots of structure. It looks absolutely amazing. So now let's superimpose Jupiter on there, on that image. So there you are on the left hand side. You can see the scale of Jupiter compared to the Orion Nebula, and it's tiny. It's tiny. It's you know, probably you've got 4 stars at the middle there called the trapezium, very well known little grouping in the middle of the Orion Nebula, and Jupiter's sort of on a par with the size of that little grouping of stars. And you can see on the right hand side here we're seeing detail on Jupiter. You're seeing one of the moons, a shadow of one of the moons. You can see the great red spot there with some detail in it. And you are working there at the limits of resolution of the telescope to pick up detail like that. So much finer than you would see in deep sky objects or imaging deep sky objects. So when you're operating at the limits of resolution, there are a lot of factors that influence what you can see or image. So let's look at some of those things. So even with everything else being right in your setup and under perfect conditions, there are limits with what you can see with a particular telescope. And it depends on the resolving power of the telescope. So even with perfect seeing conditions and you know, things that Ian was talking about, like the telescope reaching equilibrium and you know, everything being perfect, if you've got a small telescope, you're never going to be able to get the resolution that you can get with the bigger telescope. And on the left hand side there are some simulations of Mars taken with different apertures. So we've taken a Hubble Space Telescope image with very fine resolution, with a 20th of an arc-second resolution, an 18-inch telescope with a 1/4 of an arc-second resolution. And you can see that as you go down in aperture, the image becomes more and more blurred because you are limited by the size of the airy disk. Ian talked about this. So a point of light is imaged not as a point of light, not seen as a point of light, but is seen as a small disk. And the smaller the telescope, the larger the size of that disk. So you can obviously not image or see anything smaller than about the size of that disk. And then I've done the same thing again for the planet Jupiter to give you an idea of what you'd see with Jupiter. Another thing that will influence is the quality of the optics. So on the left hand side we see with a perfect 18-inch telescope, 450mm telescope. Then with quarter wave optics you get a slight deterioration. So by quarter of a wave I mean that the deviation from a perfect parabola, parabola is a quarter of the wavelength of light, of green light. And then on the right hand side, and a quarter of a wave is really regarded as the sort of the standard for telescope optics. So they should be the deviation in the wavefront should only be a quarter of a wave away from that of a perfect parabola, and that requires the surface to be within 1/8 of a wave of the perfect shape. So because the light, if you've got a deviation which is 1/8 of the wavelength away from the perfect parabola, it's got to travel 1/8 of the wavelength back more, and then got to travel forward 1/8 of a wave. So that changes the wavefront by a quarter of a wave. And then on the right hand side you see quite a noticeable deterioration in the quality of the image with half wave optics. Ian talked about thermal equilibrium of the scope, and that's a really important thing, is to let the telescope cool down. If you're keeping it in your house, it can take several hours to cool down to ambient temperatures. Much better to keep it in a shed outdoors or in a garage or something like that if you can, in the afternoon before you're planning to observe. That will help keep it, get it part way down. And then when you get it out into the environment, then if you've got a fan on the telescope, switch that on, just uncover it, let it cool down naturally. So as we've said, the view of what you can see is influenced by many things, but one of the probably the largest thing of all, the biggest effect of all, is the quality of what's called the seeing. So the atmosphere is generally in a constant state of movement, and you've got air of different densities, and unfortunately that means of different temperatures, and that means you've got different densities of air, and they'll have different refractive indices, and that upsets the image. It's similar to looking at a distant view over a hot road in the summer, and you can see the way that you know, the distant horizon is broken up and shimmers, and you get that to a lesser degree, but you're talking about very fine limits here. So the seeing has got a massive effect on how much you'll see for a given scope once, you know, everything's cooled down and it's properly adjusted and collimated. If seeing is terrible, then even the best planetary telescope in the world won't perform properly. So here are some images of Mars taken through my 444mm scope, 3 consecutive days in 2014, and you can see how the conditions vary, with very good on the 16th of May, allowing you to see a huge amount of detail. And you can see on the right hand side there, in that image on the 16th of May, the pronounced gibbous phase, and you can see that objects, there does seem to be some sort of 3D effect. You're picking out relief there, because you're getting this grazing illumination that Robin was talking about. But on the 14th of May and the 15th of May, the seeing was significantly inferior to that on the 16th of May. Okay, and so now I'm going to, we've talked about seeing, and we've talked about optical excellence, and we've talked about scope cooling. But as seeing is such by far and away the biggest effect and the biggest variable here, I'm going to show you some videos of planets taken under different conditions, just to give you an idea. Hopefully this will work okay. Can you see that? Can you see the video? So that's a video of Mars. Okay, so that's in poorish conditions. And then we'll do Jupiter. So you can see, hopefully there, see the great red spot. You can see, hopefully, you can see the direction in which the air is moving past Jupiter. So you can see it almost as if you're looking through a stream at an image of Jupiter that's laid in the stream bed, and the stream of the atmosphere is running past from left to right, from right to left. So that's Jupiter. And then here's Saturn. So again, so you get these gross movements where the whole planet is shifting around, and you get shimmering, and you get distortion, and you get blurring. So there's multiple effects going on here. But you can see, you can see quite a nice image of the rings there. So now let's look at something a bit better. So here is Saturn in the infrared. So if you view in the red or the infrared, you find that the seeing effects are reduced generally, and quite often you can get much sharper views by imaging in infrared than you can in visible light. And here you can see the dark Cassini division going all the way around the planet. So when you can see it passing in front of the planet here on the video, so in imaging the planets, you take a long duration video that creates lots of frames, and you then take all those frames and process them, and I'll be talking much more about this afternoon. When you combine those into a single still image, but you start with a video. So planetary imaging, modern planetary imaging, uses this video technique. So let's have a look now at Jupiter on a very good night. So this is a really excellent night in a couple of years ago, well, a few years ago, when Jupiter was much higher in the sky. And you can see a huge amount of detail there in the preview image. And this is before I've done any processing. So this is an unprocessed video. This is how it would appear on the screen while you were taking the video. You've still got some gross movement, but that may be caused by the scope being buffeted by breezes. And then a more recent one, which is Mars. So this is a Mars from September last year, in the infrared. And you see in the middle there the Solus Lacus, the eye of Mars. And here you've got part of the Valles Marineris, the huge rift valley that you've got on Mars that's much larger than the Grand Canyon and the polar caps. So you can see loads of lovely detail there. And when you see something like that in the preview, you know that that's going to process up very nicely and give you a highly detailed, final master image. Okay. So those are some of the key factors. There are also other factors that affect what you can see and what you can image, and the biggest thing there is experience. So for visual observing, it's a combination of your eye and your brain and training that combination to pick out detail, and that takes time. If you're just starting in planetary observing, and compare that to what you can see compared to somebody who's been been observing planets for many years, they're able to pick out much more detail, and that just comes from practice. Picking out you've got those fleeting moments of good seeing, and you can suddenly see a wealth of detail, and the image sort of builds up in your brain of what you're seeing. Lots of people will, who are seasoned planetary observers, will sketch planets and record that, and you get some quite impressive drawings that we'll see shortly. And the same with imaging. What you're able to produce in your final image depends very much on your experience, your setup, but your processing methods. Okay, and as an example of that, here's Jupiter. So this is some of my first images of Jupiter on the left-hand side, and then exactly the same telescope, exactly the same quality. They both cooled down. The nights were similar seeing, but you can see how, with improvements in technique and camera technology, how the appearance of Jupiter is so superior on the right hand side some 7 years later. Okay. So now we've got a more realistic view of what we might see or image. What do planets look like in different telescopes? And let's compare what a visual observer would see versus what you would image. And as a vehicle for exploring what a visual observer would see, I've got sketches here from visual observers, various visual observers. So starting with Mercury. Mercury is a small planet, and it never strays far from the sun. So if you do want to see it in a darkish sky, you've got to see it around sunset, or just after sunset, or before the sun rises, depending on whether it's an eastern or western elongation. So the best evening appearances, as Robin said, are in the spring, in the evening, when the ecliptic makes its steepest angle with the horizon, or in the morning. It would be autumn time if you've got a western elongation. So observing Mercury, you can observe Mercury when it's higher up in the sky. Obviously the sun is up there then, The advantage of doing that is that it is above the most disturbing effects of the atmosphere. So when a planet is low down in the sky, you're looking through a greater thickness of atmosphere, and the seeing is generally much worse. So allowing the sun to climb in the sky, and Mercury with it, allows you to look at the planet when it's higher in the sky. You've obviously then got the risks of the sun nearby, and it's not something I would recommend for beginners, and you really do need to make yourself aware of the dangers, because one glimpse of the sun and through a telescope which doesn't have any protection over the front will instantly blind you. It will burn the back of your retina. So you do have to be careful and take appropriate precautions, but to those that persevere, you can see details on Mercury. Here's a superb image taken only a few days ago, drawing. So these are sketches done by David Gray up in Northumberland, I think, and he's done some amazing drawings here of darker and lighter features on the rocky surface of the planet Mercury. So it does have features that can be seen, similar to what you'd have on the moon, darker and lighter areas, and in good conditions those can be glimpsed. Not many people do draw the planet Mercury because it's extremely hard to find in daytime, especially as a crescent. It becomes very, very dim and very hard to find. So what can you see with imaging? So I've done a fair bit of Mercury imaging over the last few years, and I use a 222mm Dobsonian, so just under 9 inches in diameter, and image in the infrared. And here on the left hand side is my image, and then, you know, okay, it's just spots and dark areas. You know, is that real? Is that just noise? Well, generally with Mercury images, what people do is you would take a simulation that's based on images taken by a previous probe messenger, create a simulation for that particular time and date, blur it, and then compare it with the image that you've created. So that's the blurred simulation image in the middle and my image on the left hand side. And you know, there's some agreement there between the darker areas and the lighter areas, showing that those are, you know, likely to be real features. Onto Venus. So Venus is larger and higher than Mercury, but the clouds render it essentially featureless. So when observing in the visual, all you see is just the phase. You see a very bright object, but you can't see through the clouds, and details on the cloud are very hard to pick out, except by the most experienced observers in the best conditions. But looking at Venus, you know, and enjoying the phase is, you know, it is a really wonderful object to look at, especially when it's a very thin crescent. So here are some drawings that I've done of Venus. This was back in 1975 when I first got into astronomy, with a 3-inch refractor that I still own. This is from Finchley in North London, and I did some drawings in the summer of 1975 when I was 14 years old. And then more recently, I took some images of Venus to try and sort of create the same thing. So this is in 2015 with my 222mm scope, and you know, clearly you can see the phase quite nicely, but no surface details on there. Observers like Paul Abel here, visual observers and sketchers of the planets, can pick out darker and lighter features in the cloud cover. One common thing that's seen is this brighter caps at the top and the bottom, sort of bright cusps that you see there. That's quite a common thing to see, and these sort of diagonal banding, darker banding on there, quite often in a Y shape on the surface. In the UV, however, can't see in the UV, but you can image in the UV, and with the UV filter, that then allows you to see quite readily cloud details. You can see the bright, particularly on the left-hand side, the brighter cusps top and bottom, and see some of these cloud features on this, you know, variations in the brightness of the clouds on the planet. So imaging Venus has been a bit of a speciality of mine over the last few years, and last summer I did some specialized imaging of Venus, and here you can see the planet as a crescent on the 19th of May. So this was about 2 weeks before inferior conjunction there, showing a very nice crescent. And then a bit earlier last year, showing some very detailed cloud structure there in the planet. So here is an image just 2 days from an inferior conjunction. This was with a 222mm reflector, so not huge. Venus was 3 degrees from the sun, so just 6 diameters away, 6 solar diameters away. And this was 2 days before inferior conjunction. And here you can see how, when you are this close to inferior conjunction, the horns become extended, and a day or so either side of inferior conjunction or at inferior conjunction, you can sometimes make out a complete circle, and that's due to light being scattered through the upper atmosphere. So the sun is basically the other side of the planet, and it's being illuminated from the far side, but light can come through the higher levels of the atmosphere and you know, extend the horn. So rather than 180 degrees here, you know, it's probably like 240 degrees or something like that. The key thing that I was concentrating on last year was to image Venus in the infrared at 1000 nanometers. And at those wavelengths, the atmosphere is transparent. There's a window there, and that allows you to see infrared emissions from the surface of the planet, because it's hot. It's you know, around about 450 degrees centigrade, and that means that it's giving off some infrared radiation. And here, this is a composite image from many nights of observation to reduce the noise, and you can see there the night side of Venus in the infrared. Darker areas are higher up and cooler, and some images have seen brighter spots on the surface of the planet, which may be associated with volcanism using this method. Particularly Wesley and Miles in Australia have been doing some of this imaging, and they were very helpful in giving me advice last year with this very difficult imaging, which is done in just after the sunset, with this 1000 nanometer filter. So on to Mars. So Mars is one of the most rewarding planets to view. You can readily see details. You're looking at the actual surface of the planet, but unlike the Moon or Mercury, which is pretty much unchanging, there are lots of things that happen on Mars. It's got seasonal changes, the polar caps there that ice deposits, you know, water ice and carbon dioxide ice, they change in size. There are changes in the dark areas in response to changes in moisture and as a result of dust storms, which can happen on the planet. The winds whip up the very fine dust, and that will change dark areas and obscure them for a while. And you can see clouds. You can see clouds in the atmosphere. You can see morning mists and quite dense clouds. So there are lots of things that happen on Mars. The tilt changes. Mars is quite hard to observe from one particular perspective, and that's the fact that oppositions, because it's going around in its orbit at a similar sort of speed to Earth, it takes a while for Earth to catch up with it. And oppositions, unlike most the other planets where you get oppositions every year, Mars oppositions occur every 26 months. But because Mars's orbit is noticeably elliptical, the distance between the Earth and Mars varies quite significantly. So you can see here how far north Mars is varies, and also the size varying. So when it's furthest, an opposition where it's furthest from Earth, say as in 2012, it'll be down around 14 arc seconds, whereas in 2020, the opposition we've just had, it was over 20 arc seconds. There's a little picture there, column there showing you the relative size of the planet, and obviously the area that's presented goes with the square of the diameter, so it makes a really big difference to what you can see. But the other factor is how far north it is in the sky for us northern observers. The best apparitions favor those southern hemisphere observers, so it's closest to Earth. You can see in 2018 there, when it was closest to Earth and the largest, it was well south of the equator, so was very low from the UK. The more recent apparition last year, much further north, 30 degrees further north in the sky, so much higher up in the sky, but just slightly larger. And this repeats, this same thing repeats over those sort of cycles. So always it will be the southern observers that get the closest apparition, and generally for those in the northern hemisphere, it's the one after that closest opposition, 2 years after that, that's got the best balance between size and how high it is in the sky. So here are some drawings of Mars that I've done, and you can see quite a lot of features. You know, the contrast is reasonably high. If you have good seeing, you can see the polar caps, and here you can see the dark wedge-shaped feature of Syrtis Major. That's with a 3-inch refractor, quite a small telescope. When I was just 12 years old. More recently, in 1992, I did a sketch with a 10-inch Newtonian telescope, and that wedge-shaped feature of Syrtis Major is on the left-hand side there. You can see, obviously, you see more detail in the bigger telescope, but there's plenty to see and draw in the small telescope. As a more experienced observer, a huge amount of fine surface detail can be seen, and here are some sketches by Mars BAA Mars guru Richard McKim, you know, absolutely fantastic amount of detail that he's picking up there and has committed to paper. And here are some images from 2012 and 2014 showing a very similar face of Mars, and again showing you the effect of aperture. So with the smaller telescope, you don't get the resolution that you get with the higher telescope on the right hand side. You know, there's a factor of 2 difference there in the aperture, and they're both taken in very good seeing conditions. On the left hand side, you see much more obvious cloud details and morning mists on the right hand side. And in both cases, the dark spot on the right hand side are volcanoes poking through the cloud layers there. And then more recently, so yes, this slide just shows you the varying tilt of the planet towards the Earth. So I've added in an image from just last year there, where you've got the South Pole tilted towards the Earth, and then on the left hand side in the middle, then the North Pole at the bottom there. These are inverted images, tilted towards the Earth. So you can see the sort of changes that happen. Jupiter, so king of the planets, presents a larger diameter, a larger angular diameter than any of the other planets except Venus when it's closest to Earth. That is larger then, but otherwise it's Jupiter that's the biggest. And you can see a wealth of detail in good conditions for all scope sizes. So going back to my venerable 3-inch refractor again on the left hand side back in 1975 from Finchley, there showing the equatorial belts and some temperate belts there, quite a lot of detail. And then 10-inch Newtonian in the middle showing the great red spot, and then on the right hand side through my current largest telescope, my 444mm back in 1999. And again, here's some drawings done by Richard McKim showing, you know, that with the right equipment in good conditions, it's just almost too much to draw. And occasionally you get that, you know, you look at these planets and there is just too much to draw. And because Jupiter's rotating quite fast, you have to work fast. You know, in an hour, there are quite significant shifts. It will have rotated 1/10 of a rotation, which is quite significant. A lot of these features would have significantly moved position. So yeah, a real skill to pick out the detail and to be able to rapidly put that down on paper accurately does take quite a bit of experience, but it does show you the level of detail that you can pick up visually. So Jupiter does change as well. You can see some views here over the years of Jupiter. You can see, for example, in 2010, the disappearance of the south equatorial belt, which happened for a period. And you can see, you know, changes in the coloration of the great red spot, and you can see, you know, some minor belt changes and things. So yes, there are local changes, spots and things that appear, but there are some quite gross changes that happen on the planet as well over the years. In 2012, you had a very strong belt at the bottom there, a temperate belt at the bottom that was visible.
I've muted it.
Hello. I think we've got some noise there from Brian Watson. Did you have a question, Brian?
I beg your pardon. No, just trying to have some lunch.
Do you want to mute yourself?
Well, I thought I was muted.
No, you've come unmuted for some reason. There we go. Lovely. Okay. So here's what can be seen, like we did with Mars, with different scopes in very good conditions. So here we've got an image from 2012 with a 222mm scope, and then in 2015, what you can see with a scope of twice the size there, and you can see the improved level of resolution. You know, you're picking up quite significant detail in the great red spot there, both under very good seeing conditions. And here's my best ever view, my best ever image of the planet Jupiter from 2016. Saturn, the most captivating of the planets, because of the rings, you know, quite spectacular to see, spellbinding really. Although the globe itself is usually fairly bland, you can see belts on there, but not an awful lot changes. But very spectacular. One of the key things that does change is the tilt of the rings. So that was an image from 2015. 2010, however, the rings were edge on, and that happens every 13 years. So here you can see, this is an image from the 5th of September this year, and you can see quite a lot of the details with the rings. I mean, you'll be able to see these visually, some of these visually, and image them. So you can see this very obvious break in the rings between the outer ring A and ring B, and that's called the Cassini division. Ian made reference to Encke's division, which you get glimpses of here, which is this little dark separation here. You can also see the crepe ring, which is this quite transparent ring just inside ring B. So it's very faintly visible here, but you can probably see it more clearly with the planet itself as a background there. So you can see this darker thing is not a band on the surface of the planet like this is. It is much more, it's the ring, the crepe ring itself. And another feature that you can see here, which is quite unusual at the moment, is that you can see at the top there, you can actually see through the globe, you can see through the rings, and you can see how the outer ring A actually is not opaque like ring B is, but it's translucent, so you can see the south pole of the planet through the rings here, and that's quite a strong phenomena that you can see at the moment, but you don't normally see that. It's to do with the particular geometry that we've got at the moment. Occasionally you can get things that are a bit more exciting on the planet. Large storms can break out. So here's from 2011 showing a quite disrupted northern temperate region there, where a large white spot appeared and then became spread out around the planet. So what can you see visually? Here with different instruments are some views of Saturn showing the crepe ring, even with the 3-inch refractor. You can see that, some belts on the planet, and then just finer resolution stuff. In large telescopes you can see a tremendous amount of detail. So here's a sketch from David Gray from 2003, quite an old, but and the rings well presented to us, and the planet high up in the sky. But yeah, absolutely incredible. amount of detail seen on the surface, and you can see all these different ring features. You can see the crepe ring, you can see it projected against the globe of the planet, you can see belts and all sorts of stuff. Absolutely amazing. So let's close now with talking about the ice giants, so Uranus and Neptune. You can see there the various sizes of the different planets, which depend on the distance between Earth and the planet, and it can vary quite a lot, particularly for Mars. We talked about from about 3.5 arc seconds up to 25 arc seconds. So you know, a factor of sort of 7 in the size. Uranus and Neptune, really very small, 3.5 to 4 arc seconds for Uranus, and 2 to 2.5 arc seconds for Neptune. So for a small telescope, that's, you know, you're getting towards the resolving power of a small telescope with planets of that size. But some experienced observers can actually see surface details on the planet Uranus. And here we see some banding, some vertical banding there. Uranus is quite unusual in that the polar axis is tilted right over at 98 degrees. So you can look onto the, you know, you can see the pole of that tilted right over, and that means that any banding on the surface is vertically orientated. So here's an image of Uranus that I took back in 2015 in very good conditions on Halloween night. So this is a composite showing 5 of its moons there, its brightest 5 moons, with a different exposure than the planet, and the planet there with the North Pole on the right hand side. I think it's the North Pole is the brighter area on the right hand side there, and some of the larger belts on the planet. So this is an image taken in infrared with an infrared filter, and that does allow you to see these banded features, and then I've then colorized that to match the visual appearance. And even Neptune, you can see details on the planet Neptune. Not heard of anyone actually visually seeing anything on the planet, but spots and things like that can be occasionally seen on the planet. And this is from 2017, where some amateurs with larger telescopes were able to see lighter spots on the surface and follow them as the planet rotated. And here's some spots between over a half-hour period, showing them rotating with the planet. So yes, is it a reasonable expectation to see the planets as we see there? Well, it's not reasonable, but you can come close. And here's a composite image from 2018. Yeah, that I took in 2017. So these are images taken in 2017, arranged there, and that was the year when there were spots on Neptune. So I've got detail on every planet in the solar system except Earth, arranged there into that parade of the planets. And I think that's it. Thank you very much. So shall I stop sharing now, Robin?
Martin, yes, if you could stop sharing and then go to your participants and make me the host again, that would be good. Thank you.
Host.
Now, if people have got, I am the host now. Thank you. That's great. That's super, Martin. Thank you very much indeed. Now, if people have got questions, the best thing is you go down to the bottom of the screen where it says reactions, and it says raise hand. And so I will use that as an indication that people have got something to ask, and then you're welcome to open your video. Steve, go ahead, Steve. There you go.
Oh, I pressed the right button this time. Great talk, Martin.
Thank you.
Fantastic. I was particularly impressed by the images of Venus and Mercury, and I know you do sort of daytime imaging a lot.
Yes. Yes.
I guess I wouldn't say it's safe, but it's safer to use a Newtonian in that situation. So the tube acts as like a sun shield to stop the sun going onto the primary.
Yes, I mean, what I do is I have a screen on a pole. So I have an illuminized screen that's about 1 meter by 0.5 meter on it's an extending paint roller pole, 3 meter paint roller pole, and it's 3 sections, so you can move it up and down. And then it's on an umbrella parasol base, and I move that around and orientate it so that it blocks the sun from the telescope. So yes, you don't want it's obviously sunlight hitting the primary, because then it'll burn the camera. But also you don't want sunlight entering the tube at all, because what it will do, it'll warm the inside of the tube and create tube currents and those convection currents will destroy resolution. So you have to shield it from a safety perspective, but you also have to shield it from an imaging resolution perspective if you want the best images. And sometimes that's quite difficult in the summer when the sun is high, Mercury's high, and I've got this screen, you know, like 12 feet up in the air. And then if it's a bit blowy, it all gets a bit hairy.
Yeah,
So,
when I've done that with a Dob, I check the weather forecast for clouds, and I also check it for the wind.
yes.
You don't want the wind catching the scope at the wrong moment.
No. And when I took that image of Venus when it was 3 degrees from the sun, that wouldn't have been possible earlier in the day, because because when you're that close, the screen's got to actually be quite a distance from the telescope for the geometry. Otherwise you start blocking the aperture of the scope. You want to block the sun. So it's got to be like 5 meters away from the telescope. So if the sun had been up in the air, I would have had to have a screen that was like on a pole that's like 10 meters long. It would have been absolutely ludicrous and unworkable. But this way, with the sun in the evening, the sun was lower. I could have the pole down the garden 5 meters away, and then I had to tether it because it was blowy. So I had to put guy ropes on the screen to stop it blowing around. It was all quite difficult, but it all worked out. It all worked out nicely. And because it's so bright, Venus, it was, even though it was just 3 degrees from the sun, you could see it in the finder scope quite easily. Whereas Mercury is just a nightmare, because it's so much dimmer that you can be, you're looking there, you can't see it in the finder, you've got a low power eyepiece in there, Mercury is in there somewhere, and sometimes I've searched for an hour and a half in a sort of 1 to 2 degree area, and I've just given up.
Yeah, I've never been able to find Mercury during the day. I've just got a go-to Dob, so I hope that will solve it. So we'll see.
I think you'd leave the Dob or the go-to telescope aligned from the night before, wouldn't you? Would be able to find it.
Yeah, that's true.
Which is another matter. Catherine's got a question. Catherine, over to you.
Yes.
A regular visitor to Preston Montford. Glad to see you here.
Yes. You clearly demonstrated the effect of having a smaller aperture compared with a larger one. And now, if you could actually model the effect of the smaller aperture, which I believe is using something like convolution, you can actually mathematically solve this and actually get rid of these degradation effects. the algorithms to do this are not very good at the moment. Do you think it's a situation that could improve in the future?
Well, you're always going to be limited by the size of the airy disk, you know, so that puts the physics puts a hard limit on the smallest features you can see, because you know any feature is always going to be blown up to the size of the airy disk. So you can tighten things and improve the contrast, and if you've got very high things, so like Encke's division, yes, that's below the size of the airy disk, but it's just a contrast effect. You could never, you know, in most telescopes, you could never image the width of the Encke's division or anything like that, but you could see it because it's a high contrast effect, and that's why you see it. But no, I think you're always going to be up against the physics of diffraction, really.
Okay, thank you.
Okay, any other questions? That was very comprehensive talk. Thanks very much, Martin. Right, well, we've got a lunch break now. I had hoped that we might have some offers of solar observing. Either nobody's got any sun or nobody's got planned for solar observing. It's quite a challenge to do that live streaming, so we can't offer that. Usually we have lunch at about 1 at Preston Montford, and I can hear the dinner ladies clattering away now already. So we will have a lunch break now. Now, after the break at 2 o'clock, we've got Lee Fletcher talking about the atmospheres of the giant planets. And that will be great because we will be able to find out just what it is all those squiggles and blobs and spots actually refer to. So that will be a unique opportunity. We always like to try and get somebody who knows what they're talking about at Preston Montford, and we've got Martin, we've got Ian, and now we've got Lee. So he will be coming along just before 2 o'clock. So I will leave I'll leave everything open. If people want to chat, that's up to them. But we will look forward to seeing you again at 2 o'clock, and I'll put a caption screen up for the time being. So see you then.